Okay, so if you don't have any questions about this, actually everybody in the room right now is successful in the course in the sense that everybody in this course has got a C or better so far. Please keep that up. That's actually optimized. If you've got any questions about the exam where you're standing, you can come and see me. So, any questions? All right, so I'm going to start this class off with a little bit of a teaser here. Who wants to do this problem? Right? I mean, this, you know, this is like death on a hot plate, right? Nobody wants to do this powerless thing. But this is actually not too bad of a problem. This motivates all section. We're going to talk about matrices that can be diagonal. And I'll be precise about what that means. But first, let me point out the easiest matrices in the world to deal with. The very easiest matrices are the scalar matrices. They're the ones that look like this. And let me make clear that I'm going to square matrices. Easy square matrices. They're called the scalar matrices because they're just a scalar, lambda, times the identity matrix. What nice properties do these have? Why are these easy to deal with? Well, one of the things that I think is easy is this multiplication of scalar matrices is easy, right? So if you have a scalar matrix, you multiply by A, it's the same thing. And in fact, multiplication of a matrix by a scalar is just multiplying everything in the matrix by whatever lambda is, right? So it's very easy to manipulate multiplicative, right? Doesn't matter what order you do it in. And in fact, multiplication by a scalar matrix is just basically, so if I multiply by the matrix, 2's down the diagonal, times any matrix, it's just taking that matrix and multiplying by 2. So these are the nicest. The second easiest are the ones that are diagonal. They're not so quite as nice as scalar matrices because the values along the diagonal can be different. However, they perform nicely. Let me point out that if you multiply two diagonal matrices, order doesn't matter. So if you have, let's say 2, 0, 0, 3, 4, 0, 0, 5. This matrix multiplied out is 8, 0, 0, 15. And this is the same thing as 4, 0, 0, 5 times 2, 0, 0, 3. Now you have to be a little bit careful because this does not mean the diagonal matrices commute with every matrix. They do not. So for example, for example, if I have 2, 0, 0, 3 times 1, 2, 3, 4, this is 2, 4, 9, 12. On the other hand, this matrix is actually different. This is 2, 6, 6, 12. So diagonal matrices are not quite as good as scalar matrices because they don't necessarily commute with them, they commute with each other, right? Which makes them, their multiplication a little easier. So let me take you back to my challenge problem here. So suppose A is, just for example, this 3 by 3 matrix I had 5 minus 4, 2, 4 minus 3, 2, and 3 minus 4, 4. And suppose I wanted to compute the 6th power of A. And that's so easy, right? However, right? Notice that now, for example, A to the 6 is right. So if I want to figure out what's the 6th power of A, I'll have to do the 6th power of this. Now this might look like, well, Jim, you must be crazy because this one's worse, but it's actually not. Well, of course, so far, 2, 3, 4. 6. Right, that looks worse, right? But it ain't. Does anybody see? Does anybody see something you do? And it might have helped if you've ever had accordion lessons. What?
The P inverse of the G is
and this now squeezes down P to the 6th power. Now, if this is a diagonal matrix, computing the 6th power of a diagonal matrix is pretty easy, as a matter of fact. In fact, it turns out, in this case, that my A, this matrix here, 5 minus 4, 2, 4 minus 3, 2, and 3 minus 4, 4. It turns out that A is equal to P, the inverse, and I'll write down the players. Right here. In this case, I believe my P is minus 2, 2, 1, minus 3, 2, 1, minus 2, 1, 1. And my P inverse is 1 minus 1, 0, 1, 0, minus 1, and 1 minus 2. Now, of course, the first complaint you might have is, okay, Jim, where did you get these two matrices here? And don't worry, I'll tell you. This is what today is about. And the diagonal matrix is that. Now, if I want to compute this, notice that what is d to the 6th? Quickly, so this is the P, E, the inverse. What's the 6th power of this? It's just the 6th power of the diagonal matrix. Right? So it's 1 to the 6th, 2 to the 6th, 3 to the 6th. Much easier computation. So this matrix actually 1, 0, 0, 0, 64, 0, 0, 0, 7, 29. And so the answer to this conundrum I'm sorry? Yeah, but 6. So in this case, a to the 6 is p d to the 6 p inverse, which in this case, my p is minus 2 to 1, minus 3 to 1, and minus 2, 1, 1, 1, 0, 0, 0, 64, 0, 0, 0, 7, 29. And then the inverse of P, which is that trailing matrix, 1 minus 0, 1, 0, 1, and 1. So really, all you have to do is multiply these 3 matrices. And it's much easier to multiply these 3 matrices. Like, for example, the first step here is, I won't finish this really, but it's -2, 128, 729, -3, 128, 729, and -2, 64, 729. And you can do the rest of this, but it's basically easy. I mean, multiplying this by this means just add this row up, etc. And it's much easier than doing computations with 6 power that first makes them. Okay. What made this computation work really nicely was the fact that A could be conjugated from a diagonal matrix. Right? So, without further ado, let me give you the definition, the theme for today. And again, in this section, square matrices. We're always talking about square matrices. Definition. So it's supposed to be an n by n matrix. A is called diagonalizable if it is similar to a diagonal matrix. More precisely, that is, A is PDP inverse for some diagonal matrix. So this is what we mean to say that something's diagonalizable. It doesn't mean it's diagonal, but it means that we can conjugate a diagonal matrix and make it that. Or conversely, we can, this is the same thing as saying that P inverse A P is equal to D. We can conjugate A and make it a diagonal matrix. And sometimes that's good enough to do some important computations. Now, here is the big theorem. The question you might ask is, are all matrices diagonalizable? Example. This example, the non-example is the interesting part here. This matrix is diagonalizable. In fact, it's diagonal, for crying out loud, right? So in particular, you could take the matrix P to be the identity. It's already diagonal, so of course it's diagonalizable. But I don't have to change this very much to make this not diagonal. Is not. Not only is this matrix not diagonal, but no matter, you can never find an invertible matrix P such that, in a diagonal matrix D, such that this matrix is conjugate. Can't be done. And I'm going to give you a theorem that will allow you to see this fairly quickly. We'll do some examples of this. So the big question is, which matrices are diagonalized? That is, which matrices can be conjugated to be a diagonal matrix? And I can answer that in the following. Suppose you have a square matrix with real entries, but this theorem again can be generalized to other fields. A is diagonalizable if and only A has n, that is the size of the matrix, so to speak, linearly independent. So, how can we tell when a matrix is diagonalizable? Well, you can find the eigenvalues and the eigenvectors if you have n linearly independent eigenvectors. And by the way, that's the most you can have. If you have a full set of linearly independent eigenvectors, then it's diagonalizable. If you fall short, right, for example, if you have a 2 by 2 matrix and there's only one linearly independent eigenvector, it's not diagonalizable. So let me add to this theorem because what I want to add to it is going to tell you what to do in computation. So here's my addendum theorem. A will equal to P, P inverse with D diagonal. If and only if. So this is kind of an interesting add-on because in my statement here, I'm going to tell you not only how whether A is diagonalizable, but I'm going to tell you how to make the P and the D. So this is my little recipe here for making the P and the D. If and only if the columns of P are in linearly independent eigenvectors A, and the diagonal entries in D correspond respectively to D. Let me kind of outline why that's true. I'm going to at least kind of sketch over the proof, and then I'm going to get my hands dirty and write you some computations. This. Okay. Let's first start off this way. Let me point out that if so I'm going to make the statement in general. I'm not assuming P is invertible yet. I'm going to let it improve. But let's let P have n column vectors. And let D is a diagonal matrix. D is matrix here, lambda 1, 0, 0, 0, lambda 2, 0, 3, 0. Okay, so my setup here is this has n column vectors of height n, right? That's my P, and this is D, right? Notice that AP is equal to A so when I take the matrix A times this matrix P, then it's A times these column vectors, which the new columns and the new product look like this. So this is what AP looks like. On the other hand, if I multiply PD, well, P is this thing, and D is this big mess here. What happens when I multiply this through like this? Well, this has columns that look like this. So, what does that tell me? Well, I've sort of set you up here. We're doing this computation here. So if let's say that A equals P, P, P. That is to say, let's suppose that A is diagonalizable. I am going to multiply on the right side of P so if this equation holds, in this equation, and if AP is equal to PD, that means these columns pair on. So this means that AB1 equals lambda 1 C1, comma, AB2 equals lambda 2 B2, all the way out to ABN equals lambda 2 B2. So the B1, B2, Bn are eigenvectors. For eigenvalues, respectively, lambda 1, lambda 2 of the lambda 10. Because that's what it means to be an eigenvector. And in addition to that, the i's are linearly independent. Because P is invertible. Because what we have is, by assumption here, P is invertible, and P is made up of these columns. I know these columns are eigenvectors, and if P is invertible, these columns have to be linearly independent. So therefore, that's kind of the first statement there. On the other hand, if we have linearly independent eigenvectors corresponding to these eigenvalues, you can just kind of run this in reverse and see that you get that A is diagonalized. Okay, any questions on that before we kind of get our hands on some computations? Okay, so let's do this. You know, I gave you this crazy matrix to start off the class today. Let's pull it apart and see if we can get what I claimed earlier. We started with this matrix here. So this will be kind of good practice for us. 4 minus 3, 2, 3 minus 3, right, it was this problem. So my instructions here diagonalize that. Okay, so I want to follow kind of the recipe of what I wrote down. So the first thing I'm going to do is I'm going to find the eigenvalues and the eigenvectors. All right. So okay, so let's take the determinant of this. Okay. And since it's only 3 by 3, I'm going to put this out. Okay, so I need the determinant of this. So this is the product of this, which is minus 12, that's plus 3 lambda minus 4 lambda, plus lambda squared, and then plus 8. You guys better watch me on this. Next bit, plus 4 times the determinant of this matrix here, which is going to be 16 minus 4 lambda minus 6. And finally, plus 2 times the determinant of this matrix here, that's going to be minus 16. And that's going to be 9 plus 3 lambda. So we'll see what I get here. This is 5 minus lambda. This is lambda squared minus lambda minus 4. This is 4 times minus 4 lambda plus 10. And this is 2 times 3 lambda minus 7. Okay, so I'm going to kind of do some stepping here. Well, I'll go ahead here. 5 lambda squared minus 5 lambda minus 20 minus lambda cubed plus lambda squared plus 4 lambda minus 16 lambda plus 40 plus 6 lambda minus 14. And let's pray that I did this right. This is minus lambda cubed. Okay, what do I get for lambda squared? I get a plus 5 plus 6. Agree. Let's see here. What do I get for lambda? I get negative 5 plus 4, so that brings me negative 1, negative 17. That looks like negative 11. And what do I get for my constant? I get minus 20 plus 40 is plus 20 minus 14 is plus 6. Perfect. Now, if you remember what I did in the problem, you probably have a clue what's next. But what do we do now? This is the determinant thing. We set this equal to 0. Try to find the eigenvalue, right? Okay. Goodness, I don't seem to remember the cubic formula. Can somebody help me? Oh, you got a calculator. Does anybody know what the rational root test is? How many people have heard of that? It turns out that when you have integer coefficients, so polynomial like that, in fact, yeah, integer coefficients, the only possible rational roots. Now, there's no guarantee that roots are only rational. The only possible rational roots are factors of the tail divided by factors of the head. So the factors of the tail are plus or minus 1, plus or minus 2, plus or minus 3. Factors of the head are plus or minus 1. So the only possible roots of this are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Am I okay with that? Does anybody see one that works? So we're solving this equation here. Lambda cubed minus 6 lambda squared plus 11 lambda minus 6 is equal to 0. Notice I changed the sign, but since it's equal to 0, it doesn't matter. Anybody see a root of this? Yeah. 1 is a root, right? Because 12 minus 12 is 0. That means the universe is speaking to you. That means that has to be a factor of this. Has to be, since 1 is root. And now I'm going to play Dick Tracy and kind of take what's left over. This is lambda cubed minus lambda, and this is plus 6. So it's going to be lambda cubed minus 6 lambda plus 11 lambda minus 6. How about this? Well, now you can get roots from this from the quadratic formula if you like. You can see basically the roots of this. Yes. So I've got 3 eigenvalues. 1, 2, and 3. Right? So let's get the eigenvectors. Lambda equals 1. Well, let's see, so subtract this. 4 minus 4, 2. 4 minus 4, 2. 3 minus 4. 3. Okay. Notice these 2 rows are the same. Actually, since this is a non-student's eigenvalue, you should have a null space. So let's reduce this. I'm going to put this on the top. 3 minus 4, 3. 4 minus 4, 2. And actually, I'm going to get rid of this row. 0, 0, 0. Right? Because these 2 rows are the same. And I'm going to add minus 1 times this row to this row at the top. I'm going to put this row in the middle now. Minus 1 times this row at the top. 1, 0, minus 1. And now I'm going to use this to take out the middle one. 0 times minus 3 and add. Minus 3 and add. And 0. So notice I have 1 free variable. X3 is free. And so my eigenvector was like x1, x2, x3. And I get these equations here. X1 minus x3 is 0. And I get minus 4x2 plus 6x3 is 0. So this is x3. X2 is actually minus 2, or is actually 2/3 of x3. And x1 is x3. So this is x3 times 1, 2/3 of 1. And to make it look more like my matrix here, I can multiply this by 3. 3. Yeah, I'm glad I checked that. This is wrong because x2 is actually 3 halves x2. Right? Is that what you catch me on? This should be 3 halves. So this should be actually 2. There. For 2, let me go back to my equation here. I'm subtracting 2 off of this. I get 3 minus 4, 2. I get 4 minus 5, 2. And I get 3 minus 4. Notice that I have these 2 rows the same, so I'm going to make the bottom row of zeros. So I'm going to kill one of these. And I am going to put 3 minus 4, 2 here. And I'm going to take minus 1 times this and that, this. And let me massage this a little bit further. This is 1 minus 1 is 0. I'm going to multiply a negative 3 and add. 3 and add. And this was so easy to develop. 0, 0, 0, 0, 1 minus 2. And it's going to be 1, 0, minus 2. So again, I have x3 is 3. And so I get eigenvector three. This equation gives, so, and I'll get the equation x1 minus 2x3 equals 0, and x2 minus 2x3 is 0. And so this is 2x3, 2x3. So I get x3 comes back to 1. So let me collect what I've got so far. So don't lose track of this. I got lambda equals 1. I got the eigenvector 2, 3, 2, 3, 2. For lambda equals 2, I got the eigenvector 2, 2, 1, I believe. And finally, for the eigenvalue 3, I get the matrix 2 minus 4, 2, subtracting 3 from this, 4 minus 6, 2, and 3 minus 4, 1. Right. 3 minus 4, 1. 6, 2. Okay. Right. So it must be in case of this combination. So I'm going to use this to take out the next 2 rows. Well, actually, I'm going to go 1 minus 2, 1. I'm going to cut this in half. This is going to be 2 minus 3, 1. And 3 minus 4, 1. And 1 minus 2, 1 comes minus 2 and add. And comes minus 3 and add. 2. And good, this is a singular matrix here. So I can take this row out. Minus 1, 0, 0, 0. And this is 1, 0, this comes 2 and add. And so for this one, again, x3 is free. And I get x3, x1, x2, x3 is x3, x3 and x2 are the same, and x3 and x1. Very good. So for this last bit, I have this. Yes.
So that last matrix, none of the columns or rows are multiple of each other. So, but you can still find
one of the columns is a linear combination of the others. Right? That is correct. In the first one, none of them are a multiple of each other, but there is a linear combination of these first two that equals this last one. Right? And that's revealed with the step work. So in this case, we have A is P, D, P inverse. Let me tell you how to take this information and tear it apart. My D corresponds to the eigen values 1, 2, and 3. And the P is the eigenvectors in that order, right? So for example, I get 2, 3, 2. That's the eigenvector for 1, 2, 2, 1, which is the eigenvector for 2, and 1, 1, 1. Now, if you're very clever and look back at the notes, you will notice that this is actually different from my P, and the fact that this column is off by a sign. In my original matrix, it was -2, -3, -2. That is not an issue because that's still an eigenvalue. Or I'm sorry, still an eigenvector. But you should test that this works, but that's how you put it together, just with the eigenvectors. Now, you can sometimes have multiple eigenvectors corresponding to a single eigenvalue, but that's okay, you just repeat it. So if you have an eigenvector or an eigenvalue that's repeated, just put the two eigenvectors with the repeated eigenvalue. So let me put the following note. If A is an n-by-n matrix and A has n distinct eigenvectors, or eigenvalues, that is. Then A is diagonalizable. That is to say, if you have a matrix and it turns out that you have all different eigenvalues, then it has to be diagonalizable. It is not necessary that it has all different eigenvalues. So for example, this matrix only has the eigenvalue 1, multiplicity 2, and so does this one. This is an example we looked at before. This one is diagonalizable. This one is not, because the second one has only one linearly independent eigenvalue. So let me give you this last theorem. Let A be an n-by-n matrix with distinct eigenvalues. Lambda 1, lambda 2. So these are all different. Lambda K with K less than or equal. Number 1, for all values 5 between 1 and K, the eigenspace corresponding lambda I has dimension less than or equal to multiplicity of lambda I. And when I said multiplicity of lambda I, I mean how many times it appears? That's root. And number 2, A is diagonalizable if and only if the characteristic polynomial for A factors into linear factors. And the dimension of each eigenspace is equal to multiplicity of its eigenspace. Okay. Any questions on it? Okay, so practice this stuff. I will give you a quiz probably later this afternoon that will be due Friday. And I don't anticipate giving you a quiz actually over the fall break. So you guys can have that off. And don't forget, I have a meeting from 10 to 11, so I won't be available then, but everything else is business as usual. Questions? Yes. Well, it'll now have a different inverse, right? And so you change the meaning by changing the sign. It's still similar. Yeah, that's right. It's still similar. Okay. Other question? All right. Y'all have a good one.